Welcome once again to this course on the foundations of optimization, and we had just learned about Newton's method, its properties of very fast convergence to the solution if you are starting from a point very near the solution, which is a very difficult thing, because of course you want to find a solution, you do not know the solution. So, Newton method has some sort of this guess and test business, because you start from a point in which you could be lucky that you are near the solution, in which you could be unlucky that you are far from the solution and you go further away from the solution. There are other drawbacks of the Newton method, which is, for example, this. Let me tell you what could be the possible drawback. So, the Newton iteration is of this form. The k plus 1th iteration is related to the kth iteration in the following way. This is what is called the Newton iteration, which you are completely aware by now. Now, the major issue here is as follows, that this Hessian matrix whose inverse you want to take, suppose, so if I denote this by h of xk, which is quite the standard practice in optimization literature. So, the question arises as follows. Number 1, is hxk invertible? Can you get that for functions which are not strongly convex? If a function is strongly convex, then it is all right, then for Newton method it is possibly very good for strongly convex function and it has unique minima, so it is much better. So, this is one question. Another question is, even if this is invertible, assume that it is invertible, does it mean that I will always have this as a descent direction? Shall I have this as a descent direction? That is a very important question. So, now the question is, if these are my drawbacks of the Newton method, how do I go about trying to remedy this method? One approach of remedying is possibly the following, that instead of having a matrix B, instead of having the matrix hxk, I consider the descent direction given by some matrix bk. So, instead of having the inverse of the Hessian matrix, I consider some matrix of this form. So, this is approximation to the inverse of the Hessian. You can consider it like this. When you have replaced the Hessian inverse approximation to the inverse of the Hessian. Now, you have chosen a direction of this form. So, you have solved this question by telling that I will not take a matrix, I will not have to invert the matrix, I will take a matrix which will approximate the Hessian itself, the inverse of the Hessian itself, not Hessian, sorry, inverse of the Hessian. So, I do not have to bother about inverting the matrix, but I have to really bother that if I want to write this, the direction as this by replacing this as bk, then possibly I have to check if is this a descent direction. Now, how do I know that this would be a descent direction? One guarantee of getting this as a descent direction, this is to design Bk at every step k in such a way such that Bk is positive definite at all k. So, this is what you would want, because that will give you the descent direction. So, if I take dk as this as positive definite at every k, prove that dk is a descent direction, you can take it as an homework. So, if Bk is positive definite, which I am writing in short PD, at each k, then dk is a descent direction. Now, once I know this, now the question is, how would I construct that Bk? How do I know how to construct? So this whole gamut of the story of constructing Bks, of course you can start with the initial one, could be the identity matrix itself, because okay, that is easy, but then at every step we have to update and get a new Bk, and the new Bk should always be positive definite. This thing gives rise to a whole gamut of methods called the quasi-Newton methods or quasi-Newton method. Which are quite powerful and actually used in softwares. Now, we are not going to discuss right away quasi-Newton methods. We are going to show you some way of constructing Bk using the Hessian itself, and we are going to then go into some simple and beautiful method called the conjugate gradient method, which possibly is one of the not only beautiful, very powerful method for solving at least convex optimization problems and even some non-convex optimization problems, of course differentiable ones. So, now one way of constructing Bk as given in the book by Lars Christian Boyers, I would like you to take down this example, and this book is available as an Indian print. It is called Mathematical Methods of Optimization by Lars Christian Boyers. So, one of the books we would be using while discussing is the following: Mathematical is published in India by Overseas Press. The author is Lars Christian Boyers from Sweden. If I am not wrong, I guess he is from Sweden. Yeah, he is from Sweden, from Lund. And it is published by Overseas Press in India. What Christian Boyers suggests, Lars suggests to us. He said, okay, you could possibly choose Bk as follows: I is the identity matrix plus the Hessian. So, he is not inverting the Hessian, he is adding an multiple of the identity matrix, and the new matrix he is inverting, and calling that matrix Bk, where epsilon k is the least number which makes all eigenvalues of epsilon k I plus h x k larger than some specified positive constant. So, what does this mean? This means that I choose epsilon k in such a way that I can make the eigenvalue of this matrix larger than a fixed some specified positive constant, which means that for some k, for some epsilon k value, this matrix would be positive definite because all the eigenvalues would become positive, and hence its inverse would remain positive definite, and hence then Bk would be positive, and then you could possibly choose but the interesting fact that you really do not go to invert matrices, because matrix inversion is a very costly operation in a computer. If you want to invert a matrix, it takes a lot of memory space and all those sort of things which computational experts would call costs of computing. So, people want to avoid matrix inversion. So, in order to do that, one can actually write this whole thing as follows. I can write this as, this is absolutely simple manipulation, writing Bk and then writing Bk as this and then doing this. So, I can write this. So, this could be my modified Newton equation, and then what one can do is break up this matrix, because it is a positive definite matrix. I can break up this into lower triangular matrices. I can decompose into lower triangular matrices. So, this is called the Cholesky decomposition, and that is how people actually solve it. I am not going into the details. You can see in any book on numerical linear algebra. So, this matrix is lower triangular matrix, is a lower triangular matrix. I am not going into details of how you arrive at such a result. So, that is not our job here. So, this is one of the ways to do it, but now we will go into a very interesting approach called the conjugate gradient method. It would look, its name might look very strange. We are having descent directions and all those things. Suddenly, we are coming to something called conjugate gradient. See, the problem is, people knew that it is once you are out of the steepest descent business, it is not so easy to generate descent directions. So, there was a whole lot of story for developing quasi-Newton methods or quasi-Newton methods, and there is also a story of not bothering so much about directions of descent, but developing certain directions along which you will definitely reach the minimum. At least you will definitely reach the minima for the quadratic case in finite number of steps. That leads us to what is called the conjugate gradient method or conjugate direction method. So, let me talk about the or rather I would say, instead of conjugate gradient, I would say conjugate direction. That would be possibly better here, though ultimately we will come to something of conjugate gradient method. let me say conjugate direction method. Now, before I close off the discussion on Newton, let me just give you a small homework. I think you should be able to do it. So, the homework is as follows. Consider the function f x which is a quadratic function where q is positive definite. Now, if that is the case, show that I can reach the minima of this problem. You know, this minima can be very easily computed. So, show that the minima can be reached by using the Newton's method in just 2 steps. So, that the minima or minimizer can be reached using the Newton's method in just 2 steps. So, please note this homework. Now, we will speak about the conjugate direction method. So, we will start talking about conjugate directions. We will use a combination of 2 books to discuss about this, and these 2 books are available in India. So, I am using the 2 books which have Indian editions, because I want to also encourage the viewers to buy these books and follow the talks accordingly. So, there will be certain things in the books which might not be very clear to you, and it might be very clear to you when you listen to these lectures. So, it is very important that I maintain books which are available in the Indian market. That is what I think I can do, because numerical optimization is something which is been used by many users, not only mathematicians, they are used by engineers, they are used by many other people, physicists or biologists, whoever. So, this would have a large audience and books must be available. So, you cannot just learn by listening to lectures, because lectures would skip, lectures would give you homeworks and all sort of things, but books would allow you to delve a bit more in detail. And so, as a result of which I would like to use books which are used, which could be obtained in India. Now, another book which I am going to use along with the book of Christian Boyers is the book called Practical Optimization, Algorithms and Engineering Application by Andreas Antonio and Wu Sheng Lu. It is a Springer book. So, I would like to tell you the publisher, the Springer. So, this book is quite useful. I will also use very soon the book by Roger Fletcher, the legendary Roger Fletcher, one of the greatest optimization geniuses in the world. So, he is sometimes called the optimization wizard. So, I would now start discussing conjugate detection method from this particular book. Now, so when are two vectors distinct, d1 and d2, two vectors, say d1 and d2 are two non-zero distinct vectors in Rn. In Rn, whatever, I do not mind anything, you can say Rm, Rn does not mind, and H is a real symmetric matrix n cross n, of course, or m cross n. Now, when are these two vectors d1 and d2 said to be conjugate with respect to the matrix H? So, d1 and d2 are said to be conjugate with respect to the matrix H if d1 transpose H d2 is equal to 0. So, of course, I can write d1 transpose H d2 as d1 inner product H d2. Now, it is very important to know what sort of concept this concept of conjugate direction this is generalizing. Did this concept come out of the blue, from the air, somebody discovered it, or there is something else which is involved here. So, that would lead us to notion of what I called an elliptic norm. Now, if you have two vectors, say x and y in Rn, so x y is in Rn, we say that x is perpendicular to y or y is perpendicular to x if the inner product of x and y is 0. That is the meaning of perpendicularity of two vectors, that is the inner product is 0 because cos 90 is 0. Okay. Now, if you look at it, look at this definition, it is some sort of a perpendicularity. Now, what sort of perpendicularity it is? Now, if you look at, let me define, now consider this sort of inner product where H is positive definite. Now, if I write this is what is called, see, the norm square with respect to the positive definite matrix H. It is again positive definite. So, it is sometimes called the elliptic norm. Now, it is your homework to prove that this satisfies, this thing satisfies all definitions of the norm. So, consider this as your second homework today. Now, I can say that x and y are perpendicular with respect to H if x H y is 0, that is in this particular norm it is 0 in this particular set of inner products. So, if this is 0, if x, h and y is 0, then we can say that x is perpendicular to y with respect to h. Possibly we can invent a symbol like this. Now, okay, it would be more meaningful to have h positive definite because we can associate a norm with it, because norms or inner products always induce norms. So, here this could be taken as some sort of true inner product. So, inner product between x and y now. So, inner product between x and y I can write in terms with respect to h. So, this also is an inner product, it satisfies all the properties of inner product. So, this inner product will only induce a norm if h is positive definite, but in general, to make a slightly more general definition, we take h to be just a symmetric matrix, real symmetric matrix, and define conjugacy. So, d1 and d2 are essentially some sort of perpendicular vectors. So, they are because we cannot just say perpendicular, we use the term conjugate. Maybe this symbol could be used to denote conjugacy, right. So, now let us see what is the, so extend this definition beyond two vectors. A finite set of non-zero distinct vectors d0, d1, dk are said to be conjugate with respect to the real symmetric matrix H if di H dj is same as di transpose H dj is equal to 0 for all I not equal to j. Then I will now ask a few questions as homework again. So, you need to do something on your own also, not just listen to the lectures, because that is the way you learn a mathematical subject. So, the answer is, what would happen if one chooses H equal to the identity matrix I. So, that is one thing, and the second problem is, suppose these d0, 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 d1, dk are actually eigenvectors of H, then what is the relation between the vectors? So, if the vectors are eigenvectors of H, what would happen? So, you have to find out what would happen. Tomorrow I will tell you the answers, but I will not tell you the way to do it, because the thing is so simple. Okay. Now, we will talk about conjugacy with respect to a positive definite matrix. Now, in this definition of conjugacy we will consider H to be positive definite matrix. So, H now is a real symmetric positive definite matrix. So, once I have this, I have the first fundamental property of conjugate vectors is linear independence. If non-zero distinct vectors are conjugate with respect to H, where H is real symmetric and positive definite. Okay, I did not write out where are the non-zero distinct. Symmetric and positive definite. Then the set of vectors are linearly independent. Then they are linearly independent. So, that is what I want to now show you. So, let me show you that okay, if I have a system now D0 are conjugate, now consider this expression, well, some lambda j is some scalar. Suppose it for those scalars I would have this from j equal to 0 to k, that is alpha 1 d1, sorry alpha naught d naught to alpha k tk, that is equal to 0. H of summation j equal to 0 to k. So, this is by the property of matrices that you really can figure out yourself. This is by the property of matrices. Now, once you have this, now do this, take this inner product. So, what you would have again by the property of inner products, sorry, not this is not dj, this is di. So, you am taking the inner product with respect to di. So, it will become di h dj. So, an alpha j here. Now, for all those I which is not equal to j, this is what you would have when this would become 0 by the conjugacy definition. So, this will become alpha I di h di. And this is 0. Now, H is a positive definite matrix, this is nothing but the norm with respect to H, and di is non-zero. So, you would have summation alpha I, sorry this would be gone. So, it will be just this because all the other terms are 0. So, basically because of the positive definiteness of H, because H is positive definite, di and di is non-zero, implying alpha I is equal to 0. So, you can take here some other I, say d1, so you will have this, d2 you will have d alpha 2 is 0, d3 you will have alpha 3 is 0, and so on and so forth, and that shows that the conjugate directions when H is positive definite is linearly independent. Let me now show you, today's class we will end by showing you an example of how to find a conjugate direction, say two conjugate directions, two directions they are conjugate with respect to each other. So, take this matrix H, so is the example given in Christian Boyers, names are quite difficult. Now, this is a positive definite matrix, okay, and as a homework show that H is positive definite. Then let D naught be the vector 1 0 and say D1 which I want to find is say some AB. So, let us see what happens if I do 1 0 . So, this is what would happen if these two things are conjugate with respect to this matrix. Of course, they have to be linearly independent. So, this would imply that so I can take A is equal to then this equation would be satisfied for T some real number. T is a parameter, actually T is a real number. Now, put T equal to 1, then also it will be satisfied. So, if I take D0 as 1 0, now I can take my D1 as minus root 6 4. So, these two are conjugate with respect to this matrix H, and these are of course you can see not linearly dependent, they are linearly independent. Now, using this idea of conjugate directions, we can show that it is very simple to minimize a strongly convex quadratic function over Rn, in the sense that it is in n steps. See, these are not descent directions, I am not telling that conjugate directions are descent directions, but even they are not descent directions for the quadratic case in n steps without any sort of inversion of the positive definite matrix which defines the quadratic function like this, no inversion of the Q there on the board. You can show using conjugate direction that in n steps you will reach the solution, and that is exactly what we are going to demonstrate in tomorrow's class. Thank you very much.